All right, yeah, you don't have to write this down. It's stuff you've already got in your notes. Plus, I went ahead and put this as a PDF. These 3 slides here is listed as a PDF on our website under Wednesday, this quiz review PDF. So these three slides are up there. So the quiz is over 3 sections. One was parametric equation. We're going to do some of all of these today during class time. So the parametric equations, where we talk about x and y equations to describe the position of something. The slope of its path is that equation. The speed of the particle on the path is that equation. And so be able to answer questions about that. Of course, then we've got our optimization problems, like today with the business packet, maximum type problems, list of candidates, that kind of thing. And then, of course, the new thing here with the related rates. And then I added this little thing here about do not plug any values that change in until after you've done the derivative. Right? Any numbers that aren't changing, you can put in right away. But any numbers that are changing, you put variables for those. So I made a little note of that. So anyway, you've got access to this on the website. So as you study, get ready for the quiz next week, you've got those things there. All right, so let's start looking at the problems in the book, the related rate problems, like number 4. Let's go through that real quick here. So number 4 was the lamp post and the person walking, creating a shadow. Now, you had on the facing page, on page 252, they worked out this exact problem just with a different number, so you could just pretty much copy what they did. But let's talk about it and make sure you understand what's happening there. I've got a kind of a picture of this. It is kind of a fun one to look at. But anyway, you've got, so it's this problem right here with the lamppost, the man, the shadow in black. The green would be how far he is from the lamppost. And we put this in motion. Kind of like that. Walking. Yeah, I don't know, but you know, whatever. Kind of nice. So anyway, you get, you know, you don't need an animated drawing to be able to do it, but it kind of helps. But there's a couple of questions here that, and one of them that's not even asked in number 4 that we want to talk about. And so in number 4, it talks about how far away is he at a certain time, but then it asks how fast is his shadow lengthening, right? And I think in the book they call this X here, the green distance, and they call the black distance S for his shadow. So how fast his shadow lengthening would be S prime, right? That would be the rate that the black segment is increasing. And then what would be the green segment, X prime? What would that represent? How what? Well, no, that'd be, X would be how far. Yes. What would the rate of change of the green be, X prime? How fast he's walking, right, in relation to the lamppost, right? So that would be his speed. Now notice what I like about this is you notice, and you've probably seen this, so it's not like anything brilliant or anything, but when you walk like that, your shadow grows, right, faster than you. So in other words, the green segment is changing at a constant rate, but the black is getting bigger and bigger and bigger at bigger and bigger chunks, right? It's growing faster as it goes along, whereas this is staying constant, how fast it's changing. So, but the question that's not asked, that is often asked in problems similar to this, is that red dot. How fast is the tip of his shadow moving? Is that the same as the rate that the black segment is increasing? Or is that different? What do you think? I think it's different, right? The rate that the red dot is changing or moving is a combination of what? The green and the black, right? Because really the tip, because actually you could think of it this way, the tip of the green is moving, that's how fast the green segment is increasing, right? And you can imagine a tip here, but in relation to this point, right, is growing. That's how fast his shadow's growing. But the red dot is really from here to here, right? It's that length. It's X plus S. It's kind of like I use the example in the other class. You're driving down the interstate at 75 mile an hour, and you eat an apple, and now you want to throw the apple core out, right? Which that wouldn't really be littering, would it? Yeah. But at least it'd be biodegradable, right? At least it would, not like a piece of paper or something. But anyway, you're going 75 mile an hour, and you drop an object out the window. How fast is it going when you drop it? 75 mile an hour, right? But if you're driving down Interstate 75 mile an hour and you reach out the window and you throw it ahead at 10 miles an hour, how fast does it move? 85 mile an hour, right? The 75 you're going plus the 10 mile an hour you threw it. It's 85 mile an hour. So that's kind of what this is, right? The red tip is growing on the end of the black, the shadow, but it's also moving at the rate that the green one is moving. So sometimes you're asked that question, is what rate is the tip of the shadow moving? That's different than at what rate is the shadow lengthening, okay? So understand that if you see a problem like that, which you might, right? So as we go through the rest of this week, the idea is that we don't have a lot new to show, really. It's just looking at all the different types of problems and getting better at setting them up in these different scenarios. So that's really what we're after. So at number 4, it looks very much like this. So they tell you got a 12-foot lamppost. So that is not going to change. As the man walks, he's 6 foot tall. That is not going to change. So we can go ahead and put those numbers in to our diagram. They had called this X, and they had called this S. So yesterday we talked about Pythagorean theorem, we talked about some area equations, we talked about perimeter, we talked about volume, right? We had all kinds of different formulas. Well, here they talk about similar triangles. This is another thing that you sometimes can use to help you set up equations. In this particular case, the big triangle is similar to, you remember the old angle stuff from geometry? It's been a few years for many of you. But two angles in one triangle are congruent to two angles in another triangle. They are going to be similar triangles, which means their sides are in proportion. So 12 over x plus s, which would be this long side, is equal to 6 over s. And so you can now use that to set up an equation. And now we can simplify that a little bit and divide by 6. And we actually get a quite simple expression or equation that x is equal to s. So in this particular case, because the man is half the distance or half the height of the flagpole, it's actually a pretty simple one, that as he walks, his distance away is going to equal the length of the shadow. So that actually makes things pretty easy. But right there is when we would do the derivative. I can't plug any other numbers into that. They ask the question, they say, how far is he, how long is his shadow? Is that what it is? How long is his shadow when he's 10 feet away? So that's x equals 10. I don't want to put a 10 into the picture here because it's a changing value. So that's usually something I write off to the side. And then it also says that he is walking at 7 feet per second. What would that be? X prime would be 7. Okay, so those are the things I know. And then it says, how long is his shadow? So we want to know what S is. Well, we just put a 10 in for X, so that'd be easy. So S is 10. Okay, so you just put a 10 into that equation. And then at what rate is his shadow lengthening? Well, that would be S prime. We're trying to figure S prime, so I need to do the derivative of this, right? What's the derivative of X? Very good. Not 1, it's x prime, because we're doing the derivative with respect to t, dx dt. So x prime equals s prime. So, again, pretty simplistic scenario. So if x prime is 7, so is s prime. So his shadow is lengthening at the same rate that he is walking. Okay, so this would be a situation where it's, it's the same. It's not a changing amount. Okay? All right. So let's go on to number 7, and then again we can do the tip of the shadow, and that'd be 7 plus 7, be 14, right? The tip of your shadow would be moving at 14 feet per second. All right, let's look at number 7, which talks about the rectangle, and this is the one that we were doing the other day. We kind of went through a little bit. If this rectangle, if I'm drawing with my mouse, if I'm dragging with my mouse and this rectangle is growing, I can't put any numbers into this picture because everything is changing. The area is changing, the length is changing, the width is changing. So I want to set up some equation that relates that because they asked me for A prime. That's what they're asking for. They told me several things. I could write all these down, I suppose. The width is increasing at 2, so that's W prime. The length is increasing at 3, so that's L prime. And aren't they both increasing? So they're positive. If it said decreasing, we'd put negative. And then it wants to know when the width is 4 and the length is 5. So they give me tons of information, which is good because when I do the derivative, I'm going to have a bunch of places to plug things. You're going to see in a problem in a little bit where we don't have near as much information. And so we got to think about how we handle it. But in this case, it's pretty obvious. It's just going to be a simple old area equals length times width. We want A prime. We got all this information here. So we go ahead and do our derivative. And how do we say we have to do this? Product rule, so L prime W plus LW prime. And now we simply, it couldn't work any better. Everything we want, we have. So there's 3 times 4, and there's 5 times 2. And then the only thing you got to make sure you do is put the right units on it. What is that? Yeah, because it's area. And again, we know that because the L prime here is 3 centimeters per second, and the W is centimeters. And so when we take L prime times W, when we multiply those two, that's going to be centimeters squared per second. So it wouldn't hurt you to put your units on your numbers as you go. I'm not going to make you do that, but make sure your final answer has those units on them. Okay? So that's about as easy as it gets right there, number 7, when it comes to related rate problem. A nice, pretty easy formula to set up. You got to remember to do the product rule, which that can be tricky. And then they just give you all the different numbers you need to plug in. Okay? So that's nice. All right, let's look at another related rate problem. And here's, let me, we're going to do one here in a minute. Just look at this. Here's another kind of typical one. You got a cone-shaped water tank, and we're going to fill this water tank. And so the questions would be, you might be asked, how fast is H changing? How fast is R changing? Those are both changing as the water goes up. The volume is changing in this case as well. And so this question asks, how fast is the water level rising? If you know how fast the water is going in, 2 cubic centimeters per minute. So that would be V prime. So what would H prime be, right? We're going to do a problem. We're going to do a similar problem to this here in a second, okay? So let's do that. I've got a couple of them here. One is, again, water. Now this problem says water is draining out of the tank. So now the volume is draining out of the tank at 2 cubic meters. So that would be V prime, but it would be what? Negative 2, right? Because the volume is decreasing. Okay, so the tank looks this way when it's like a water tank, when it's holding something. But the problem we're going to do is this one. And this is about sand being poured on a beach, and then it creates a cone-shaped pile. Like, I always think about Shelton. When you drive on Highway 30 and you come around the curve coming out of Shelton, and there's a big grain elevator there, and a lot of times there's a big pile of corn sitting there, in the fall especially, in a big cone-shaped pile. Seems like there's always one there when you drive by there. I always think of that when I do this problem. But so this is a pretty common problem. Seems like you run into this on the AP test a lot. I don't know why the cone-shaped problems are so popular, but We want to make sure we do a few of those. So before the quiz, you'll have done a number of these. Okay? So draw yourself a picture, maybe something like this. And actually, the picture probably doesn't help us a whole lot here. But notice the very first sentence. The very first sentence says, it creates a cone where the radius is equal to twice the height. It says always equal to twice the height. So I'm going to write that down. One thing about a cone, you talk about similar triangles, that would be the case, right? As this grows, as this cone, actually it would probably make more sense for me to go back to this other picture real quick. As the water fills, you can see how you're going to have similar triangles. Matter of fact, this problem words it a little differently. This problem says the cone or the tank is 16 meters high, or centimeters, and it's 4 centimeter radius. Well, doesn't that create a similar triangle? The cone being the red, and the water creating the blue. And so what you'd have is R over H would equal 4 over 16, right? Or in this case, 4H would equal 16R, and so R would equal 1/4 H. So in this problem, the radius is always 1/4 of the height, right? So that would be true in any cone. There's always going to be this relationship between R and H. Now, I point this out because most related rate problems, you don't have to do this. Most related rate problems, you do not have to substitute one variable for another, right? That was optimization. We did that. We always wanted to get everything in terms of one variable in optimization. So we always had these secondary equations we would substitute in. But we don't normally have to do that with related rate. Matter of fact, we just got done doing a problem where we had all kinds of variables in there. L primes, W primes, A primes. And as long as we had a bunch of information to plug in, that was fine. See? But in this problem, so back to the cone. So in this problem, we know they tell us that R is equal to 2H. So that's kind of like what I just got done saying in the other problem where R was equal to 1/4 H. Somewhere in the cone problem, you will have that information that will be useful. Now, we'll see here in a little bit why it will be useful. All right, so let's read the rest of the problem. If the sand is poured at a rate of 20 cubic inches per second, so what could I label that? V prime. That's volume. The key is cubic inches. And is it positive or negative? Positive, because the sand, the volume is increasing, so the V prime has to be positive. Okay, so V prime is 20. How fast is the height changing? So what can I label that? H prime. So that's what I'm trying to find. At the time when the height, and we'll just do one of these, when the height is 2. So that would be H. So at some point in time, as the sand is piling on here, the pile will be 2 inches tall. Now, this is not changing in the problem, but this is, right? The height is always changing, right? So I do not want to plug a 2 in for H until way later, right? Because that is changed. All right, so what equation? So notice I have very little information, and notice there's no information about R. I mean, forget this for a second. So what equation could I have that would relate these variables? Volume of a cone. Anybody happen to know the volume of a cone?
That's a sphere.
That's a sphere, 4/3 pi r cubed. It's related to a cylinder. What's a cylinder? Pi r squared h.
3/4. 3/4.
Well, it's less, right? It's 1/3. It's 1/3. If you took a cylinder the same height as this, you could fill 3 of those with one cone. I used to do that when I used to teach geometry or pre-algebra. We had a cone, fill it with water 3 times, pour it in the other one, and sure enough, it would fit nicely. So that is the formula. Now, do you have to memorize that? Well, we'll do it. You'll have done enough cone problems that by the time we get to the quiz, if there's a cone problem, you probably will know it pretty easily. But up, I may put it in the problem too. Okay. So, area of a rectangle, some of those very simple ones, Pythagorean theorem, stuff like that. Obviously, I'm not going to tell you. Something like this, probably just put it in there. Okay, so that's the volume of a cone. So I can't plug a 2 in right now, right? Because that's changing. What we said in our notes here earlier is any amount that's changing, you do not put in until after you've done the derivative. Okay, so we do not plug a 2 in for h right now. So what can we do? Do the derivative of that. Now, I will caution you, and you can write this down if you want, but I'm going to work this one 2 ways, and I think the second way is going to be easier. But you actually can do it either way. So right now we could do the derivative. So let's do it. Now, if you don't want to write this down, this is probably the longer of the two, but it's up to you. So we can do the derivative of this right now. When we do this derivative, how are we going to do it? Isn't it going to be a product rule? Because r is a variable and h is a variable. They're both changing. So we are going to have to do a product rule. Now, I would suggest keeping the 1/3 pi together with the r squared and then treating the h as the second thing. That's the easiest way to do this. Okay? So let's do the derivative of the first. So 1/3 pi r squared, what's the derivative? 2/3 pi r prime. So you do the normal derivative, you tack on an r prime, and then you leave the h alone. Plus 1/3 pi r squared, derivative of h prime. So now, after you've done the derivative, now it's time to start plugging in stuff. Right? Now the problem becomes, we only have 2 things to plug in. And we're going to have some things we don't, but we can get them. So it does work to do it this way. The reason I'm not a fan of this one is because people will screw up the product rule, it seems like, and sometimes make a mess of this. But it will work. Now, when we did the area one, we had no choice. We had to do the product rule. I mean, there just was no choice. We had to do that. This one, we do have a choice, and so that's why I like to show this to you and see. And that might be why the cone one is such a popular one on the AP test, because it's got this kind of extra little bit to it that you don't have to do in a lot of related rate problems. So let's start plugging stuff in. So we'll put a 20 there. In place of r, I don't know what to put right now. In place of r prime, I don't know what to put right now. But in place of h, I can put a 2. Right? Plus 1/3 pi, and again, in place of r, I don't know what to put, and h prime is what I'm looking for. Right? So my dilemma is I need something to put in for r, and I need something to put in for r prime. Well, that's where this information comes in. Right? So if r is equal to 2h, what can I do with that? Plug this 2 in for h. And so when the height is 2, what's the radius? The radius is 4. So that helps me. I can put a 4 there for r. So that tells me that r is going to be 4. So I'll write that down over there. So I can put a 4 in place of that r, and I can put a 4 in place of that r. Correct? And now all I'm missing is r prime. I can do the derivative of this as well. So r prime would equal to h prime, right? Regular derivative of 2h is 2, tack on an h prime. So I can put in place of r prime here, I can put 2h prime, because I don't know what h prime is, right? That's what I'm looking for. So r prime is the same as 2h prime, so I can put that right there. So now I've got it down to, the only thing left is h prime, which is what I'm looking for, right? Now, you could type this into your calculator, but I think we can get it here. We got 2/3 times 4, that'd be 8/3, times 2 would be 16/3, times 2 would be 32/3. So that's 32/3 pi h prime plus, this would be 16/3 pi h prime. Oh, those are like terms. I can add those together, can't I? So I'm going to get 20 equals what? 48 thirds pi h prime. Now again, at some point, if you're not confident in this, you could have put this in your calculator instead of h prime, called it x, and solved for x, right? You could have done that. So now I just need to invert and multiply this, so that'd be 3 48ths times 20, that'd be what, 60 48ths? And then I got to divide by pi also, so the pi would go to the bottom. I think that would be h prime. Somebody help me out with, well, that would reduce. I guess we don't need to go to a decimal. You probably would on, well, I don't know if you would on your homework. 3 goes into all that. So that'd be 20. Oh, I could have done more than that. What else goes into that? 4. 5 over 4 pi. 12 goes into each of those. So it'd be 5 over 4. So I could have done that. So 5 over 4 pi, what is that as a decimal? I'm just curious. Well, somebody on your calculator divide it. Would you? And what would the units be on this? 0.39, 398? And that's what, inches per second? Because this is height. This is height, h, right? 0.398. Okay, now, let me show you what we could have done differently, and then you can kind of decide what you think. Because every cone problem, well, the vast majority of cone problems will be very similar to this. Okay? All right, so let me erase a few of these things. Okay, we'll keep our answer up there. Okay, so let me come back to here. So at this point, and some of you may have thought of this already, so you guys said do the derivative of this, right? What would have been another option before we do the derivative?
Plug in 2h for r.
Do what?
Plug in 2h for r.
Yes. Take this and plug it in there. So we'd have had v equals 1/3 pi, and in place of r, put 2h, like so. Now, if you do that, go ahead and simplify that now. Some people will get to there and then do the derivative, and then they end up doing a product rule anyway, and then what was the point, right? Go ahead and multiply that together. So this is 4 times 1/3, so that'd be 4/3 pi, h squared times h is h. See how much easier that is? So when you have this information about r and h, if you substitute first and eliminate a variable, it's helpful. But again, that's not something you normally have to do on a related rate. In optimization, we do it all the time. You have this extra information, you plug it in so you can get down to one variable, because we had to do that when we did optimization. Related rate, we don't have to. So now let's do the derivative. So v prime would be, bring the 3 down in front, so that'd be 4 pi h squared h prime. Well, now we're in great shape, because now we got 20, we got 4 pi, in place of h we can put a 2, and there's our h prime. So 2 squared is 4, times 4 is 16, so divide by 16 pi, we get 20 over 16 pi. That looks familiar, I think I had that earlier, which sure enough, that reduces to 5 over 4 pi, and we get the same answer. Make sense? So it's, in a cone problem, you've got that r and that h in there, but they are related. Because of the way a cone works, the r and h are going to be similar in a similar triangle, kind of in proportion to each other. And so you can usually make a substitution that gets it down to one variable, then that's usually better. But again, you don't have to. You could do a product rule on this, and then use that information. Either way, you have to use this information about r and h, either to plug into r or to just eliminate the r altogether. All right, so that's a pretty typical cone problem. I think you might get a cone problem as one of your homework problems to do again to practice that. But that is that scenario. Okay? Couple other things I was going to show you. We talked about theta. We talked about sometimes, we did Pythagorean theorem, area, we just did volume of a situation. Here's kind of a cool little problem here. Oh, where'd that rainbow? Yeah, the rainbow comes from the storm, if it storms here. So the plane is flying overhead, and then, okay, so what is changing, again, as the plane flies, it says the plane is flying at 700 feet per second. So X is changing, the hypotenuse is changing, this angle is changing, right? Those are all things that are changing, but the 4,000 is not changing. So if I was going to set up a problem, so the problem wanted to know how fast is the light pivoting. In other words, what's theta prime? That's what they're looking for. What equation would you use that would involve X and theta that might be a pretty good one to use? Tangent. Now, somebody in their class said sine, first of all, and then they thought about it, and they thought, wait, that wouldn't be as good, because sine would have this over this, but this is variable too, right? So now you have two variables, and you don't really care about this variable. You don't have any information about that variable, so it's kind of like the R and the H thing. You know, now we don't have any choice in the cone. We got to involve R and H. They're both in the formula. But here we would have a choice. Use X and 4,000. The 4,000 doesn't change, so you could put it right into your formula right away. So tangent of theta would be this over this, and then you'd have an X prime, which you know is 700, and then you could find the theta prime, right? So that would be another kind of a scenario. So this is just some examples of different types of problems, and we'll see more and more as we go along. Okay, let's keep going here. Let's go to the business packet. Let's talk about some of those things. So now we're moving into the optimization realm, and you know, our max min kind of thing we're trying to find. Now, I want to talk about 19 and 20, because to me those are the ones that are more like what you would see on the quiz. Okay, I apologize for that, but that's, you know, I mean, because the other ones are helping us get ready for the quiz, but they pretty much give you everything that's there, and it could be some sort of combination. I might give you a little piece of it, and you have to come up with another. But like on 12, right, you're trying to maximize your profit. So your profit is revenue minus cost, right? So what's your revenue? Well, we'll come back to that. What's your cost? Which is that, right? So they give you the demand function, which is your price, right? So how do you get revenue?
X times price.
Number of units times the price per unit. Well, that's what the demand function is the price per unit, right? That's the price per unit, little p. So we need to take X times 50 minus 0.1 square root of X. That's our revenue. Number of units times price per unit, and then minus the cost, which you were given to be that. Okay? So that, I mean, that's, you had to think a little bit about that to get it set up, but not a whole lot, right? I mean, that's just kind of following those formulas. And now, the calculator goes a long way towards doing the rest of this, right? Now we're below the red line, right? This is a thing we're trying to maximize, profit. So we do the derivative, we set it equal to 0, we see if it's ever undefined, we check any endpoints like 0 units, maybe the smallest x could be a 0, maybe there's not a largest x could be, right? We do a list of candidates, do a number line. Now I've got these things worked out here. When I did this one, this is number 12, I got 10,000 for x. Is this number 12? Yeah, I got x equals 10,000. Now that's the only one I really had, the only candidate. Now on the answer, if you pulled up the business packet answers, these were things I just made to kind of check your work and stuff. They're not complete as far as maybe list of candidates or a number line or whatever always. So don't use these as necessarily a guide of how you want your quiz to look. It's pretty close. But like I just noticed on 12, I didn't really do anything. I didn't do a list of candidates or anything like that here. This one could be just a one candidate thing and do a number line, right, and show that it's a max. But actually, you've got to answer the question. What was the question here? Find the price. So you would need to take that 10,000 and plug it right in here, right? And so square root of 10,000 is 100. 100 times 1/10 is 10. 50 minus 10 is 40. So $40 is actually your answer for number 12. $40 is what you should charge. But the key is getting it set up here, because then it's just derivative equals 0, derivative undefined, number line, list of candidates, something like that, and then answer the question. Yes?
Well, the test blank.
have like the dollar sign as a label because of this problem that we have.
Oh yeah, right. Good point. No, again, the key would be the problems will be more like number 19 and 20, where that's more obvious. Right. Yeah. Okay. So let's look at 19 and 20. Now I'm going to give you something. I would say to you that 19 and 20 are very, very similar in how you organize them, and I think I'll give you some hints here that I think will make this a little easier for you. So the first situation we have, and they're both pretty typical scenarios, right? The price changes. That's the idea. Little p. The price changes depending on demand, how many units you have. And so really the key to these problems is finding that price equation, okay? Because the revenue is number of units, X, times the price, okay? And then the cost a lot of times is just given to you. So if I look at this situation at the radios, okay? It says that every radio costs me $60 to make. So what is my cost equation? 60x, right? 60 times the number of radios. And it says that I can charge $90 for each radio. But if or the manufacturer or whoever, if they order more than 100, they're going to give them a price break. Right, which is kind of a common thing. You order a bigger amount, we'll give you a cut in the price. So at what point should they stop offering that, though? Right, that's kind of what this is saying. I mean, you can't every time they order another radio, you give them a 10% or a 10-cent price reduction. You can't do that forever. Pretty soon they'd be free. You'd be giving them away, and there's no profit anymore. Right. So you've got to set this up. So the question is, what's the price? Now remember, we're trying to do profit equals revenue minus cost. That's what we're looking for. We got our cost already. So now we're looking for our revenue. Now remember, our revenue is number of units times the price of the radio, right? So one way to do it is just try to think your way through. Does somebody have a price of the radio, how they could get it? Now it starts at 90, but then it goes down, right? Anybody have a number there that they could explain to us, or an equation there they would feel comfortable explaining? Andy?
I'd say like 90 minus 0.1 times the quantity X minus 1.
That's beautiful. Now let's explain where that came from. Can you do that? I was writing it down here because I didn't know if you'd do any good, but you did great.
Well, so you have you start with $90 per radio. You subtract a cent.
10 cents.
10 cents, yeah, for every radio that's over 100.
I couldn't have said it better. That was perfect. That's exactly the scenario. It's $90 to start, but then it's going to subtract 10 cents for every, so the 0.10, and then for every means times the radios over 100. Well, how do you write the radios over 100? Well, if it's 101 radios, how many radios are over 100? 1. So it's 101 minus 100. Or if it's 102, it's 102 minus 100. So that's it. So one way of getting that is to just talk your way through it and write it down. Now, some of you are saying, I would never have thought of it that way. I wouldn't have read it that way. Okay, so let me give you a little hint here. In the problems we do, for the most part, they're going to be linear like that. That's a linear equation right there. For every this many changes in units, there's going to be this change in price. That's a linear scenario, right? That's what a line is. You go over this much, you go up this much. Go over this much, you go up this much, right? So when you read it, you can tell that's a linear situation. Here's a little shortcut. I don't know if it's a shortcut, but this could be a way to help you get it. What I do is I make two columns. My units and my price. And I just say, okay, so in this scenario, if I have 100 units, I've got $90 as my price. If I got 99, oh no, not 99. If I've got 101 units, I've got $89.90. And I could keep going, but I really only need 2. This would be $89.80, right? So what I do then is I just say, okay, I'm just going to write myself a linear equation with those 2 points. Can we do that? What do you need to write a linear equation? Slope and a point. So if you got 2 points, can't you do the slope? And then you do a point. So watch what would happen. So what I do is I just start writing down. I say, okay, for this many units, here's the price. For this many units, here's the price. For this many units, here's the price. I give myself a couple of points, and then I just write an equation, because that's what we want. We want P equals, right? So this is kind of like our Y here. So I would say, all right, 90 minus 89.90. I'm going to subtract my Y's, and then subtract my X's, and I get 10 cents over -1, which would be negative 0.1. There's my slope. So now my equation would be Y equals, or in this case, P equals negative 0.1 times X minus, let's use this point here, X minus 100 plus 90. Now look at that equation. Isn't that the same thing Andy had? Same exact one. Okay? I like his because then you're thinking your way through the problem, right? But this one is something you can remember, right? I mean, this is just something you kind of follow a script a little bit, and it's just, but you have to recognize it's a linear scenario, okay? And so sure enough, there it is. So that is your revenue. So now we're ready to roll. Our profit is simply that equation, revenue minus our cost, and now we do the derivative. We set it equal to 0, see if it's undefined, right? When I did this one, I got 200 as my stationary point, where the derivative was 0. The derivative was never undefined, so I did a number line, positive to negative, which means it's a max. Now, there is something else we should check here, profit. So we have our profit equation, our revenue minus our cost. So we can check the profit for 200. But where else, what would be kind of an endpoint here? What would be kind of an endpoint? Not 0 radios, because that's going to be 0. Wouldn't 100 be? I mean, because up until 100, how much are you making on each radio? $30, right? $90 minus $60. So you're making $30 every year. So your profit's going up all the way up to 100, right? So you would definitely want to sell 100. If you sell less than that, you're just giving away money because you're making $30 on every radio. So up to 100, you want to, right? But after that, then the price drops. So then the question is, now am I making as much? So I think a good idea would be to check at 100. Right? But now, if you do a number line, you can tell it's increasing and then it's decreasing, and so it is still going up all the way to 200. But it wouldn't hurt to check that. So you're making $30 a radio, so at 100 radios, that's $3,000. If you put 200 into this profit equation, I think it comes out to be 4,000. So that's where you should stop giving them the price break, right? You know, because you're going to, it's going to start going back down, your profit. All right. So the next problem is very, very simple. The next problem is very, very simple. You've got these apartments, and so your revenue is going to come from the rent, and then you've got your cost for repairs and things like that. Now, what was the cost?
36.
So the cost equation would be 36. Now let's talk about X. When we say number of units in this problem, it's number of what? Apartments that are filled, occupied, right? Now it is possible to do this one if you let X be the unoccupied, but that's a little different than we're used to. I would say you would let X be the the occupied apartment. So 36X would be your cost. Okay, so the revenue would be number of units times, and now we need the price per unit. Well, I think we can use Andy's way of thinking again here, okay? To get this, what is the price per unit or the rent? Well, it starts out being what? $540. But then it's going to do what? It's going to go up 30 for every one that's unoccupied. So what would be the number that's unoccupied? It's 50 minus X. It's not X minus 50, right? It's 50 minus X, right? Because unoccupied, so if there's one unoccupied, that'd be 50 minus 1, there'd be 49 occupied, right? Or the other way around, I guess. If there's 49 occupied, then there's 1 unoccupied, right? So 50 minus X is what would go in here. So you can just kind of think your way through this to get the price. The price is 540, but it's going to go up 30. Actually, this is kind of backwards. This one isn't the more we make that we set the price. In an apartment situation, we set the price, and then this is how many we occupy, right? We raise it 30 and somebody moves out. We raise it 30 again, and somebody moves out. Now, it doesn't actually happen that way, but the idea is from experience and so forth in an area, they know that if the rent, we can charge rent at this, and we will rent out this many apartments. So we raise it too high, people will go somewhere else, you know, and we want to find that price point where we can fill our apartments, but, you know, and not have too many unoccupied, that kind of thing. Now, again, we could do the same thing I said before. We could have an X column and a P column, and we'd say, okay, for this is occupied units, so for 50 units occupied, my rent will be $540. For 49 units occupied, my rent would be $570. For 48 units occupied, my rent would be $600, right? But I really just need 2 points. So, slope, 570 minus 540 over 49 minus 50. So that's going to be 30 over -1. So -30 is my slope. So P or Y equals -30. X minus, let's pick one of these points, it'd be 50 plus 540. Now you look at that and you say, well, wait, that looks a little different. Because this had 50 minus X, this had X minus 50.
Yeah,
but I have a -30 there. So if I distributed this, it would be the same. I'd have -30X, which is what I'm going to have here. And I would have positive 1,500, which is what I'm going to have here. So that equation is the same as thinking it through that. So any of these problems where you've got this kind of situation where it says this thing's going to change this much every time this one changes this much, that's a linear situation. And so you can do it with just sets of points and do the old point slope form, or you can think your way through it as well. Okay, so from that point, profit is simply the revenue minus the cost, and you put that into your calculator, expand it, simplify it, whatever, or don't, do the derivative, set it equal to 0. Now what I came up with when I did that, I got 33.4. So let's talk about how we would answer the question here. You can't have 33.4 units occupied. So what would you do? Well, I would check them both, right? I would plug them both back in. I would call them both candidates. You think you might round down, which it turns out you do. But you could put 33.4 or 33 into the profit equation, put 34 into the profit equation. I did that, and I saw that 33 was a little high. 33 units was a little high. Okay? And again, so you could do a number line and kind of thing. What you have is 33.4 is the max, right? I think this turned out to be another one of these parabola, upside down parabola problems. But so we're getting a lot of these one candidate kind of problems, which is not unusual. So 33 is just a little higher than 34. Neither one's right at the peak. But so 33 is a little higher. But that didn't answer the question. What was the question in 20? Yeah, what's the price? What's the rent we should charge? So we would take that 33 and put it where? Into this part right here, right? So you'd put the 33 in here and see what the price, the little p, the rent should be. And I got 1,050. 1,050 is what I got for that. Okay? So you know, again, they were a little tricky, but we hadn't been through that. So I wanted you to think about them and wanted you to look at them. And now that you've seen that, we've been able to talk about it a little bit. It's, you know, if you run into that again, I think we'll handle it a little better and so forth. Okay? So related rates we worked on a little bit here today already. And then now we've spent some time with some optimization stuff. So now let's go to the parametrics. And you're going to go ahead and just work together here. This is going to be the old Luke Skywalker problem we're going to do today. Okay? So,
disproving something? Well,
No. Now, I would say, I've already told you that this is similar to Shanghai. Now, let's review quickly. No. I don't know. I don't even remember. I got this from another teacher. I don't know. I'm not creative enough to come up with something like this.
Mr. Clark?
Yes.
Do you ever, go and like find out any details about calculus and feasible?
Yes. It's probably not going to work. Yeah, I know. Calculus. It's in April. Yeah, I can't remember now what the content might be tracking
Is it like the administration stuff?
that. Well, I hadn't gotten that far.
Ah.
I hadn't gotten that far. That was going to be a hurdle too because they never would have paid for it. So we would have had to come up with funds. But I was just saying if there was any conflict scheduled.
and we could throw
Maybe that's what we need to do. We've got enough musical people here. Maybe we could do. Maybe we should perform something to raise money to go to calculus musical. Yeah. I mean, judging from our calculus carols, we've got all kinds of talents.
Yeah, those on video or something, I never saw.
Yeah, they're up on YouTube.
Calculus.
He
Carol.
just plays it.
Oh, the calculus of music.
I wasn't there that day. I had wrestling or something.
The calculus carols or the carols? Yeah, I'll post the link. All right. Anyway, back to Luke Skywalker. Now, the key to the Shanghai problem. Or wait, let me back up. What was the Shanghai problem?
I forgot.
Well, no. But what was the?
It was the tangent lines.
If you have a tangent line.
Oh, the triangle.
Well, yeah, I know that one was triangle with a parabola, but what was the essence of it? It was a tangent line.
Tangent line that and they didn't give you a point.
Yeah, you didn't know where it touched. So any problem that is a tangent line, but you don't know the point, the coordinates of where it touches. But what you do know is maybe another point. Now, Shanghai was even harder because we didn't know we had two other points, but we only knew one of their coordinates, so like 0B or 0H and B0, right? But normally a Shanghai problem is one like this, where you don't know where the tangent line touches, but you do know another point on it. And so then what was the key to solving the Shanghai problem? Two different ways to do the slope. One way was to do the derivative of whatever the equation was, y prime, because that gave you this slope here. And then the other way to do the slope is the old-fashioned y minus 7 over x minus 3. Now the nice thing is we could replace y with this equation. So we would have all x's over here, and then y prime would just be in terms of x's, right? And then we would have an equation that had all x's in it, and then we'd be able to solve that and find where that point was. That's Shanghai in a nutshell. Okay? Well, this one is going to be a parametric equation, so it'll be a little different. But the information is still here. To do, instead of y prime, what you'll do is this, right? The slope of the parametric path. On a regular equation, the slope is just y prime. But on a parametric path, the slope is y prime over x prime, right? But then you'll also have the slope between the 2 points, and you'll be able to set them equal to each other. Now, that's all I'm going to tell you right now. You get into it, and then I can help you if you got some questions. So go ahead, get together. I mean, work by yourself if you want, or get together in a group of 3 or 4, whatever, and go through this. So the first thing you want to do is draw a picture. They give you the parametric path, tell you the situation, and go ahead and get working here. Okay? Definitely need your calculus because you're going to graph this parametric equation. So this is part of your homework for tomorrow. So hopefully you get a lot of it done before you leave here.
Team assemble.
If you get working, you probably can get a lot of it done.
I would like to be able to.
It's weird.
It's funny how the interior. All this stuff.
I think I hit the gun.
We're making like a.
I thought we were gonna make it.
I think we were just gonna do.
This robot's less like.
Jazzy can perform.
Sit on my paper.
Such a.
They never called them.
You want these dang cookies? I'll tell you want some cookies? I don't want Liz's. I'm just getting any more. I don't want it anymore. I did. I wanted it this morning. but I don't want it. It's for the macadamia.
Why is it such a